Have you ever just looked at a giant building and thought, how? Not just how it stands up, but how it even gets off the ground in the first place. Well, today, we're going to pull back the curtain on the invisible world of numbers that makes every single structure possible. I mean, just look at this thing. It's this huge tower of steel and glass just scraping the sky. It looks so permanent, right? Like it's always been there. But the crazy thing is, before a single piece of that steel was ever put in place, this entire building existed only as a bunch of calculations on paper. And that's really the heart of the problem, isn't it? How on earth do you know exactly what you're going to need? How do you count every single brick, every bag of cement, every truckload of dirt for something that doesn't even exist yet? It sounds kind of impossible. Well, the answer has a name: quantity surveying. You can think of it as the science, and really the art, of predicting the future. It's all about turning an architect's beautiful drawing into a practical, financial, honest-to-goodness plan. So, with a calculation this massive, where do you even start? You'd probably think it's with the foundation or the first delivery of materials, right? Nope, it starts somewhere way more basic, with the ground itself. See, before you can build up, you usually have to level everything. The natural world is beautiful, but it's rarely flat enough for a building. So job number one is to turn that bumpy, uneven ground into a perfectly engineered surface. And this huge job really just boils down to two simple things. Over on the left, you've got a cut. That's literally what it sounds like. You're cutting away a chunk of a hill. And on the right, you've got a fill, where you're dumping earth to fill in a low spot. That's pretty much it. Every giant earth-moving project is just a big combination of cutting and filling. Now, to do this with pinpoint accuracy, surveyors have their own lingo. First, there's GGL, or existing ground level. That's the ground as it is, natural and uneven. Then there's FL, or formation level. That's the goal. That's the perfectly flat surface they need to create. The whole job is just about making the EGL match the FL. Okay, but this brings us to the real challenge. How do you actually measure all that dirt you have to move? I mean, how do you measure a piece of a mountain you need to get rid of? It's a tough one, right? You're dealing with all these weird, irregular shapes. You can't just do a simple length times width times height. It's way more complicated than that. So how do they do it? Well, the solution is actually pretty clever, and this is the best way to think about it. Imagine trying to find the volume of a whole loaf of bread. Instead of measuring the whole thing, you just measure one slice at a time. Surveyors do the exact same thing with the earth. They take measurements at set distances, creating these imaginary slices of the landscape. And one of the most common techniques is called the average end area method. It's actually not as complicated as it sounds. You measure the area of your first slice, then the area of the next one. You find the average of those two areas, and then you just multiply that by how far apart they are. Boom, that's the volume for that little chunk. You just do that again and again and again. So all that complexity really just boils down to this one simple, beautiful formula. You take a massive irregular shape and you break it into these small, manageable pieces that you can solve with basic math. It's a really elegant solution. And here's what that math looks like in the real world. Now, don't worry about all the numbers here, but this table shows the earthwork for just 1 kilometer of road. Each row is a different slice. You can see the depths, the areas, and finally the volume for each bit, all split into cuts and fills. So what's the grand total from all that math? To get that 1 single kilometer of road ready, they had to add over 4,800 cubic meters of earth. That is enough dirt to fill almost 2 Olympic-sized swimming pools. And that's just the fill for 1 kilometer. The scale is just mind-blowing. All right, so the ground is perfectly level. Our canvas is ready. Now you take that same insane level of precision and you apply it to the building itself, to every single material that's going to go into it. Let's talk about something as basic as concrete. It's not just concrete, it's a precise recipe. For this common mix, it's 1 part cement to 2 parts sand to 4 parts aggregate. Every single batch of concrete has to follow that exact formula, or you risk the strength of the whole building. But it goes way, way deeper than just the recipe. These quantity surveyors have to figure out the total amount of everything for the entire project. And their calculations get incredibly specific. Okay, get this. For just 100 cubic feet of brickwork, that's a pretty small section of a wall. The math says you need exactly 1,383 bricks. That number is not a guess. It's a calculation that accounts for the size of each brick, the space for the mortar in between, and it even factors in a little extra for bricks that might break. That is the insane level of detail we're talking about. So why? Why go to all this trouble? Why this obsessive precision? Well, because this invisible math is the very foundation that makes all of modern construction possible, safe, and efficient. And the payoff is huge. Getting the numbers right means you control your costs, no wasting money on stuff you don't need, and no stopping work because you ran out. It cuts down on waste, which is better for the environment. It keeps these massive projects on time and on budget. And maybe most important of all, it guarantees that the entire building starts on a foundation that is exactly as strong as the engineers designed it to be. And that's really the heart of it. This isn't just some math problem from a textbook. It's the real-world, practical blueprint, both financial and material, that allows our entire modern world to get built. So the next time you see a finished building, just take a second. Remember that it's not just the result of all the visible work you see. It's also the result of all that invisible work, of the people who counted every brick and every cubic meter of dirt, before anything was even there. Because at the end of the day, the physical world we see all around us is built on a world of numbers that most of the time we don't. Kind of makes you wonder, doesn't it? What other invisible calculations, what other unseen systems are holding up the world all around you right now?